Okay. We start talking about related rates, and just to get us started, um, think about we're looking overhead at a pool of water or a pond or something, and we drop in a pebble. And I'm going to use this example because the geometry is fairly simple, and the equations they're just not too complicated. So the geometry is simple, and then we can talk about the calculus, and then we can get into more complicated geometry. So when you drop a pebble into a pond, it creates a circle, right? A ripple, a circular ripple, and it expands out. It just keeps moving out like this, right? It has a rate of change. The radius is changing at a constant rate. It's moving out at the same speed all the time. It doesn't speed up, it doesn't slow down. So a question could be about this thing is, how fast is the area changing at any given moment? Because we can find the area. If the radius is this much, then we can find the area. But how fast is the area changing? How fast is it getting bigger? And we could see at the beginning, if we let the radius increase, x, then we didn't gain much area. If we let it increase x more, well, we've gained more area than we did the first time. And if we let the radius increase x again, the same amount every time, and therefore it would translate to the same amount of time has gone by, we gain even more area. And every time we let the radius increase for some small time interval, the area increases by more and more each time. So the question is, at any given instant in time, how much area are we gaining at that moment? Because it's changing every instant. So we want to track it down and say, at that instant, how much is it changing? How fast is it changing? What's its rate of change? And when we think rate of change, when we think change, we should think derivative. We should think, how fast is it changing? What is the slope? Let's say we graph this, and at time 0 we have 0 area. Then we drop the pebble in. This is the instant that the pebble is just barely touching the surface. Once it enters, the area of that ripple gets a little bigger, but then a certain amount of time goes by and we've gained more area. And the same amount of time goes by and we've gained even more area than before. And even more area for the same amount of time, and even more area. Okay? So if we were to connect this, we see that as time goes by, the amount of area is going up and the rate of change of the area is going up. And if I wanted to know how fast the area is changing in any moment, I should think the slope of the tangent line. The slope of that tangent line, move this out of the way. The slope of that tangent line, that is how fast the area is changing with respect to time. So we want to track that down, that exact rate of change. So why don't we write an equation that relates a bunch of stuff that either we want to know or that we already know, and get ready to use that equation and take the derivative. So I know that the area is equal to pi r squared. Whatever the radius is, I square it, multiply by pi, that gives me the area. The cool thing is, let's say that I knew how fast the radius was changing. Let's say rate of change of the radius is 2 meters per second, really quite quick. Let's make it a meter per second. Barely more believable. What is this rate of change of the radius? Let's look at the radius, at the graph of the radius. As time goes by, let's say this much time goes by, the radius is this much. As this much time goes by, the same amount of time, I've gained the same amount of radius, and so on and so on, and this would be just a line. As time goes on, I'm gaining the same amount of radius for each little time interval, so I just get this line. Okay. The rate of change is the slope of this line. The rate of change is the slope of the tangent line. The tangent line would be the same as the actual line. So for this function, if this is time and this is the radius, then this is dr dt, the derivative with respect to time. So let's go back and look at this guy. I know something about the rate of change of the radius, the derivative of the radius with respect to time. And I have that here. Let's just, out of curiosity, let's take the derivative of this with respect to time, and we'll do that to the whole thing, right? So I'm going to take the derivative with respect to time, and I come over here, I'm taking the derivative with respect to time, and this is exactly implicit differentiation. We're taking the derivative on both sides with respect to some variable, and it turns out it's some variable that's not even in the equation, and that's okay, because all we need to do is apply the chain rule like we did in implicit differentiation. So the constant multiple rule would tell me pi just is going to hang out there and get multiplied by the derivative of this. This is, we're not taking the derivative with respect to t, it's with respect to r. So we need to remember to do the chain rule. Chain rule would tell me the derivative of the outside, which is, the outside is something squared, so 2 times that something, times the derivative of the inside with respect to time, that's just dr dt. So look, I have related the rates of change of the area with respect to time to the rate of change of the radius with respect to time. And say when the radius is 5 meters, I want to know how fast the area is increasing. Because remember that the rate of change of the area is changing all the time, every instant. So when the radius is 5, and the rate of change is 1, that's what we're saying here. How fast is the area changing? Well, it's changing at a rate of 10 pi meters squared per second. Quite a lot. 30, somewhere around 30 square meters. Okay, so that's a pretty simple example. The geometry is simple. The derivative is simple. The equation we take the derivative of is simple. And hopefully we see how the questions are about these instantaneous rates of change, and we use like a picture of the situation, not a video, but a picture, a frozen moment in time, to relate these two values that we will then find the rates of change of. Okay, let's go to 25 and see this example work itself out. So we've got this tank. It's actually a pool, and it's being filled with water, and it has all these dimensions. It's 3 meters on the deep end, 1 meter on the shallow end. It's 12 meters long and 6 meters wide. And if you think about it, think about when the pool was empty and it was getting filled. It was empty, and you just barely were adding. You were adding water at this constant rate, and probably it hit the bottom of the pool and spread out really quickly, and it looked like, man, it's getting filled up really quick, and the water levels started rising. But as that same amount of water, that same volume of water per minute is coming in, it's spreading out, spreading out, and spreading out, and the more space it has to fill, the slower it looks like, well, the slower it is rising. Okay, and the slower it looks like it's filling, but it's filling at the same rate always. What is changing is how fast it's coming up. If I let 1/4 meter cubed per minute go into a glass of water, man, that would fill up quick. The height would go up really quickly. If I let this same flow of water fill up a kiddie pool, it would fill up pretty quickly, but not as quickly as the pool, or the glass, sorry. And if I let the same amount of water fill into the ocean, you would hardly think it was making any difference. You're not going to see the height of the ocean rise because I was letting a quarter of a meter cubed per minute go into it. And it's the same kind of deal here. The bigger the space that volume is trying to fill, that flow is trying to fill, the slower it rises and the less effective it seems like it's being. And so our question is about that height. It's coming up really quickly down here, but by the time it's all the way up to the top, it seems like it's just never going to get filled up, right? So we're going to ask a question about how high it is, or how fast the height is changing. Okay, but firstly, we want to test our geometry abilities. And part A says, let's see, yeah, 25. What percent of the pool is filled? And that one of the pieces of information that it gives us, not on the diagram, but just in the wording, is that the water is 1 meter deep. So you got water that's 1 meter deep, and at that instant, what percentage of the pool is filled? And that would be, you know, the volume of water over the volume of the pool, you know, the potential pool, if it were completely filled. So you got to find the volume of the water and then the volume of the pool. First, we'll find the volume of the pool. And this, you'll notice, is just a prism. And a prism is any shape that we have a base or a face, however you want to think of it, and then we just extrude it out, right? We took this almost triangular shape and just pushed it back and you know, made it three-dimensional now. And we have that same face over here. We connect those two faces and we get this solid, this three-dimensional figure. And with that, remember that any shape that we do this to, we elongate, that we call a prism. For instance, a circular prism would be a cylinder, or a rectangular prism might be what we would refer to as a box. Okay? Any of these, if you take the area of the face and you multiply it by its depth or its length, whatever you want to call it, along this dimension, right? Its area times its length or depth, whatever this you call this, that would be its volume. So you just need to find the area of this, the surface area of this face, and then multiply it by 6, because that's what that is. It's 6 feet deep into the page, or 6 meters. So the volume of the pool, let's find the area of this face. Well, if we were to slice it like this, a horizontal line stemming from the bottom of the shallow end all the way across, now we have two figures, this rectangle here and this triangle here. Well, the area of a rectangle is base times height. Its base is 1 meter, or its height is 1 meter, times its base, which apparently is 12 meters. And then I'm going to add that to the area of the triangle, 1/2 base times height. Okay, the base of this is also 12. Times how high is this triangle, where this side is, the deep side is 3 meters. The shallow side is 1 meter, so we take that meter away from the 3 meters and we have 2 meters. Okay, so that's the area of the face, the little rectangle, the triangle, area of the face times 6 times its depth. That's the volume of the pool. Now the volume of the water at this instant, it's 1 meter deep, right? And this is just a triangle. This is just the area of a triangle, not of this other odd shape. So the area of a triangle, we just need to find the area of this triangle and then extrude it along. That's 6 meters. Well, it's 1/2 base times height. I've done something here. This should have been 1/2, right? This is the area of the triangle, 1/2 base times height. I left that out. So the area of this triangle is 1/2. Well, we know the height is 1. Now we got to figure out this base. Well, if you'll notice, this is going to be a right triangle. This is also a right triangle. They share this angle, so that clearly those angles are the same. If they have two of the same angles, then this angle must also be the same. So we have similar triangles, which means that the proportion of any corresponding sides are the same. So if this triangle, this bigger triangle, is 2 meters high and 12 meters long, well, that would say to you that it's 6 times as long as it is tall, because it's 2 this way and it's 12 this way, 6 times bigger. So if this similar triangle is got a height of 1, then its base must be 6 times that, which is 6. Okay, so that's the area of the triangle times, for the volume, times 6, this depth. Okay, and this is going to be our percentage. And we could cross out these 6's. And this should make sense, really, because the percentage of the volume of the whole pool that's filled by this water is the same as the percentage of the area of this triangle to the area of this other face figure of the pool. But anyhow, this would be 12.5%. I guess this would be 0.125, which we would translate to 12.5%. So they're not equal, but it does imply. This would imply that we have a 12.5% amount of the pool that's filled. That's part A. Part B says at the same moment. By that I mean, it's always being filled, and at the moment that the water is 1 meter high, at what rate is the water level rising? So think about this picture. We see its picture, it's a frozen moment in time, and so those things that we can measure in that frozen moment, let's relate them. Don't think about how fast things are changing yet. Think about a just still state. What things can we see in that still state? We can see lengths, and we can see volumes, we can see areas. Let's compare those things as as it benefits us, because we want to know something about the height. Okay, we want to find something. We definitely want to include height in our calculations. We know stuff about the volume. We definitely know stuff about lengths and depths and all that kind of stuff, which would be included in the volume. So we want to know stuff about height, and we know stuff about volume, so maybe we could relate volume and height. The volume is going to be equal to, and since it's a triangle right now, that's all we have to worry about. So the volume is equal to the area of this triangle times the depth. 1/2 the, and we want to include all basically leave it all variables. We want to leave the one, like the specific measures, until we have taken the derivative. So the volume is equal to the area of this thing, which is the height, okay, times the base, 1/2 base times height, times. Now this never changes. This is always going to be 6. So we might as well just say times 6. That's going to be the volume. The volume is going to be the area of the face times 6, always 6. So the volume is going to be equal to 3 times base times height, because 6 times 1/2. But now I don't want to include B, because I don't really know anything about B. They don't ask me anything about B. I don't have a lot of information about B, except I do have one piece of information about B, and it's what we talked about in this problem, and that is that B, the base of this triangle, is 6 times its height. So instead of writing B, why don't we write 6h? And then that would be times h. So this would be 18h squared. Alright, so we've related the volume directly to the height. If I knew the height of the water, the depth of the water, I'd be able to find its volume. But now we want to relate, well, what we really want is just to find out something about the rate of change of the height. So let's take the derivative with respect to t of both sides. So dv dt, that's how fast the volume is changing with respect to time. And then we'll take the derivative of this side with respect to time. We got the constant multiple rule telling us just to pull the 18 to the side, kind of, and just multiply it by this derivative. And this we should be thinking chain rule. The chain rule says derivative of the outside. The outside is something squared. And the derivative of something squared is 2 times that something to the first. And we're going to multiply that by the derivative of the inside, which is just the derivative of the height with respect to time. And now I can just start filling things in if I know them. Well, I know that the rate at which the volume is changing with respect to time is given right here. It's this water that's coming out. It's 1/4. And over here, I know that the height is 1. They told me that. And I don't know dh dt, but that's okay because that's what I want to find out. So dh dt is equal to, well, let's find out. We've got 1/4 divided by all of this stuff, divided by 36. So 1/4 times 36. We're going to divide by 36 on both sides. And let's see. That's 1/144th of a meter per minute. Not a lot is happening right there. It's pretty slow. Okay. So, that's the basics of how you set up a problem. You got to relate those things that you see in a photograph. That's what I try to think of. What do I see in the photograph of this thing? Not in the video, but in the photograph. A still moment in time. Okay, let's try 35. Classic stuff. A guy walking away from a lamppost. Here we go. So, a guy and a lamppost shining a beam of light and making a shadow. And this guy's walking. And so we need to know some things. It says that this is 15 meters. Or 15 feet. It says that he's 6 feet tall. What else does it say? Okay, it tells us how fast he's walking. So I like to put a little arrow telling me that he's walking at 5 feet per second. Okay. So in this photograph, we're going to see what we can see, but as it pertains to our question, at what rate is the tip of his shadow moving? So they want to know this distance. Let's call it L. Right? They want to know how fast is the tip of his shadow moving. How fast is it moving away from a fixed point? And we might as well make this fixed point where the lamppost is. So they want to know something about that. We know something about this distance from here to the man. And we know something about how fast it's changing. So we want to relate that. Remember that in this first equation, we're going to relate all of the things as variables, right? Anything that's not a constant, we're going to leave it not a constant. So somehow I want to relate this x, something that I know about, or something I know something about as far as the derivative, to this, to L, something that I don't know, but I want to know something about. So what can we do? How can we relate those things? Well, what we should see is similar to the last problem. This is going to be a 90 degree. This is going to be a 90 degree. They're sharing this angle. Maybe I'll use different colors. 90 degrees here and here, sharing this angle. So those are equal. And so these angles must then, right, if they share the two angles are congruent. The third one has to be because they add up to 180. So they're similar triangles. And I know something about similar triangles. The ratios of their sides. Say the ratio of this side, one of the legs to the other leg is the same as this leg to this leg. And let's just try it out. We know that the ratio of that side to the base, the height to the base, let's say, is equal to the height to this base. So this base doesn't really have a name, but I can give it a name. How about if I take L and subtract X, it'd be L minus X. Okay, what do I want to know about? I want to know about how fast is L changing. So let's, cross multiply, get rid of these denominators. We'll have 15 times L minus X is equal to 6L. And since I want to know something about how fast L is changing, how fast the tip of his shadow is moving, I know that means I want to know something about dl dt, the rate at which L is changing with respect to time. So let's get L by itself. Okay. So let's see, we're going to distribute 15L minus 15X equals 6L. And moving some things around a bit, we're going to have 9L is equal to 15X. So L is equal to, 5/3 X. Once I solve for L and reduce. So now take the derivative with respect to time. On this side, that's what it is. Over here, I've got the constant multiple rule. Multiply by the derivative of this with respect to time. Well, since it's just x, the derivative of this with respect to time is that. So it turns out that the rate of change of the length of the shadow, or the rate of change of the shadow as it relates to this fixed point, the rate at which the shadow is moving, not growing but moving, is just proportional to the rate at which the guy's walking, right? So apparently the shadow is moving at a constant rate as well. It's just moving at 5/3 of the rate of how fast he's walking. So all we need to do, just take 5/3, multiply it by 5, the rate at which he's moving, dx dt. So 15/3. That's pretty cool. Okay. That's part A. And part B says what's the rate at which his shadow is growing, right? With respect to himself, how fast is it getting bigger? Because we know it's getting bigger. It doesn't stay the same size and just follow him around wherever he goes. As he gets further away, the shadow is getting bigger. So how fast is it getting bigger? That's part B. Okay, we want to know something about the rate of change of this dimension. That's L minus X. Right? Well, I mean, all I know is that I want to know how fast this is changing. I want to know the derivative of this with respect to time. Well, the difference rule says that I can take the derivative of L and subtract the derivative of X. Well, this is dl dt and this is dx dt, and dl dt we just found is 15/3, and we already knew that this was 5 feet per second, so that would be let's see, this is 15/3, and that would be I see my mistake. You probably saw it a long time ago and was wondering when is he ever going to change that. That was 25/3. 5 times 5 is 25. And this would be 15/3. 5 would be the same as 15/3. So that would be 10/3. The rate at which his shadow is growing is 10/3. let's see, feet per second. Okay. And actually, I think we'll let that be it. Okay. So I hope that was helpful.